Okay, we're ready to roll. I'm Galen Shipman, again, Oak Ridge National Lab, here to try to corral these four presenters and panelists who are going to talk to us about big data. We've got a pretty distinguished group here, DK Panda, who's from Ohio State University, Milind Bhandakar, who is chief architect at Greenplum. Josh Simons is an HPC architect at the office of the CTO at VMware. And we also have Sumanta Chatterjee, who's a VP of server technologies at Oracle. And they're going to be talking about big data, mostly about big data in the commercial space. We're going to be hearing more about Hadoop infrastructures, optimization of those infrastructures, Exadata infrastructures, and optimization of those infrastructures using high-performance networking technologies. I did ask them to answer some questions around storage, but didn't get much response there, so I'll skip those. And I did get a lot of response, though, on some of the data analysis-related questions to consider. In particular, how are big data software infrastructures such as Exadata, MapReduce, key-value stores, and Memcached utilizing modern high-performance networking infrastructure? And what really is the primary challenge addressed by modern networks in these big data software infrastructures? Is it scalability? Is it low latency? Is it high bandwidth? And in particular, what are the workloads that map to those characteristics that really optimize performance? So we'll go ahead and start with DK. He's got quite an extensive slide set. We're going to see, but he guarantees he can do it in 10 minutes. So this ought to be good. But a lot of good material there. So let me pull that up. There you go.
Okay. We deal with high performance networks, so we have high throughput presentations. So. Okay, so I'll be talking here a little bit like I gave a short presentation like last year, if some of you remember. So the broad motivation, what we are working is like we know like OFED has been there, or the InfiniBand has been there for almost now 11.5 years. So a lot of work has gone into MPI. I also talked about UPC, OpenSPAM yesterday, parallel file system. We heard a lot of talks. Now, of course, now the next phase is like enterprise and commercial computing. And especially the focus is on big data and data analytics. In the Hadoop, we have SDFS, HBase, and MapReduce, and also Memcached. So the question here, what we are trying to answer is like most of the people are using 1 gig infrastructure, and there is, of course, concerns for performance and scalability. Many of the enterprise organizations are already started looking at some of these issues. So broadly, from a research angle, what we are looking at here, like what are the challenges, where do the bottlenecks lie, and can these bottlenecks be alleviated, just like what we have done for the last 11 years in the MPI context. So I see it is like a rerun of what has happened with MPI. Now we are trying to take it to the enterprise environment. So here it is a pictorial things just to illustrate the concept. So this is a complete like a open fabrics, all different protocols being used. So here we have all the sockets version. Either you go through the regular kernel space or you go through the IP over IB. And of course, we have seen some acceleration through SDPs. Some presenters talked about that. Here, the objective is to go to the right extreme, like trying to see how these things can run over IB verse. And if we can run it over IB verse, I'm sure we can also take it to the IWARP and Rocky. So those are similar. So in a different manner to make it a little bit less complex. So the current design, we are seeing like everything is based on sockets. We also have some solutions over accelerated sockets. But sockets are not designed for high performance. We have been hearing that. The stream semantics, there is a mismatch. And zero copy is not available for non-blocking sockets. So the question is, can we go through this right-hand approach? So our approach is to take this application, just like MPI design, we have a OSU design here, which will go to directly over the verse interface, and then it can run over any of the RDM-enabled networks. So we started this project with Memcached, and the Memcached is basically like it's an integral part of the Web 2 architecture with a distributed caching layer. It basically allows to aggregate memory from these multiple nodes. And these are typically used to cache database queries. results of API calls. So this is a scalable model, but when you are doing this kind of operation, there is a lot of load on this network. So what we are trying to study first, just in an isolated manner, like saying how we can take advantage of the network to accelerate these operations. I'll not go into details because we don't have time here. So this is like some of our OSU design, like we have done, and compared it with, like, let's say this is the 1 gigi numbers are here. This is the memcached gate latency for small messages. So we have the 1 gigi here, then 10 gigi. The 10 gigi line is here. And then OSU, we have multiple different designs, like a UD-based design, RC-based design, a hybrid design, just like the MPI we have done. And then IP over IB. So here you can see, like, for 4 bytes, we are able to, like, QDR, we are able to give around, like, only 4.28 microseconds. With RC or with UD, it's like 4.86. So compared to, like, 10 gigi, we get around factor of 4 improvement here. So that is the latency, but we are also interested in the transactions, because that's what, like, the memcached, we want to maximize the number of transactions. So here you'll see, like, get TPS for 4 bytes. So these are the new RC-based and UD-based design. Here you will see, like, we can go up to 1.4 million transactions per second. And here we try to scale it to, like, almost 1,000 clients. So there are different threading models. Here we are using, like, 1 threads for each node. And then after that, we have multiple threads for the same node. So that's why the performance goes down. But overall also, we can, like, improve the performance by a factor of 2 to 3 compared to the other networks. Then we evaluated this also with a benchmark called Olio. It is available in the memcached environment. So here again, for that benchmark, also we see, like, around 1.6 or 1.9, 1.7 is, like, 4x times better than the IP over IB for 8 clients. And then we worked with Yahoo. I have a previous student there, so we worked with them to come up with a capture of their application, like the marketing, how they do the advertising business, trying to take it there. And then we try to run it over this application workload. And here we see almost, like, compared to IP over IB, we have almost 12 times performance improvement. And these are some of the papers which we'll be presenting at the CC Grid in the next 2 months. So that was just the memcached. And coming back to some of the questions, when we studied the memcached, again, since memcached, like, we made the data resident, so we are trying to solve piece by piece. And then in the end, we'll try to put them together. So then in the Hadoop framework, as many of you know, like, we have the Hadoop nodes here, the data nodes and the clients. And then we also have the Hadoop as the HBase as the database component. So first we try to study again the HBase when the data is resident in the memory. I'll show some numbers. And then we are trying to really go into the SDFS layer and then trying to see how to optimize it further. So again, here the idea is the same thing, like directly from the HBase, we have the JNI interface, and then here is the OSU design, which directly talks with the InfiniBand verbs. And here if you see, like, this is a get operation with IB DDR. So we get around, like, 65 microseconds. So this is the 1 gigi number. This is IP over IB. This is 10 gigi, and this is the OSU design. For 1 kilobytes, we get around 65 microseconds. And then here we get the throughput around 15 or 11,000 transactions per second. This is a factor of 2 improvement over 10 gigi. And over QDR, we again get better performance here. So this is 1 gigi, this is IP over IB, and this is the OSU design. So around factor of 4 improvement. And in terms of operations per second, here we can go around, like, 22,000 transactions per second. Then this is the HBase. So then we went into much more detail, saying where we are gaining and where we are losing. So this is like the standard analysis you do, like how much time it is taking client serialization, client processing, server serialization, server processing, communication preparation, and communication. So here if you see, that is exactly the communication time we are reducing. Okay? So overall, you'll see that the communication time for the HBase 1 kilobyte put is like only 8.9 microseconds. So the communication perspective, we are improving by a factor of 6x. Okay? But then all other, like server time and all that, we cannot improve. Okay? So the communication here, we see the high performance network can really help to reduce the communication time. And overall also we get good performance. And this study has been done with the funding from IBM. So IBM has been the collaborator also here. And then the HBase single server, multiple client results. So similar kind of trends we see, like this is the the latency, and this is like the operations per second. We are able to go into like 37 kiloops per second or 53 kiloops per second. So we get around 27% improvement over 10 gigi. Then this is a YCSB, which is a common Yahoo Cloud Service benchmarks. Here it is the latency, and this is like the operations per second. Again, the same story, either like a 18% or 22% improvement when we scale to like 128 clients. This is a YCSB read workload. The trend is again similar, 20 to 25% improvement. And this is the read-write workload. This is also 40 to 42% improvement. So the trend exactly we see just like the previous one. And finally, what we are doing is the HDFS, which is the main component, the file systems. So we are trying to see, can that also, we can directly try to write it over verbs with using a similar kind of design. So this is just a preliminary. We have just started. We don't have all the numbers, but this is the only number we have so far, some preliminary designs. This is like the 1 gigi. Here IP over IB, this is 10 gigi, and this is our design. So up to like 2 gigabytes or 5 gigabytes, here we can do it like 14 seconds or 86 seconds. So for 5 gigabyte file size, we see almost 20% improvement over IP over IB and 14% improvement over 10 gigi. So again, once again, these are very preliminary results, but I just want to show that we have gone to that level to optimize. And as we saw from the earlier talk, like these are a lot of Java code and a lot of different kinds of architecture is there in the HDFS. So they have all been written with slower network in mind. So we need to rethink, saying how do we take the high performance networks into mind. So this is a very short presentation I did, but 2 weeks back in the HPC Advisory Council Lugano, I gave a 1-hour talk on this. So this is a video and the slides are there. So please feel free to take a look. So the concluding remarks, I just want to say that InfiniBand with RDMA feature is already getting momentum in the HPC. It is possible to use these features in enterprise environment, and I showed some initial numbers, but this is again, as I said, this is a rerun of what started in the 2002, 2003 for HPC MPI. So we need another 10 years to resolve this. Thank you.
All right, and you know he did it in 10 minutes and 30 seconds, so wow. that was high bandwidth. So, up next, we'll go ahead and move on to a bit of work by VMware. Let's see. A little out of order.
So that's fine. My intent here is to make a few high-level comments about big data and share a little bit of performance data of running some big data workloads in a virtualized environment, and then end with a couple of relatively high-level comments about the role of the internet for big data.
So Josh has been working with VMware. He's got over 20 years of experience in the HPC community, and we're going to be hearing about how VMware is bringing some of those HPC concepts to the data center and the enterprise.
Thanks, Galen. Oh, you screwed up my joke. We'll do it anyway. So normally, in most environments, the elephant in the room is usually referring to something that everyone knows about. It's very awkward, and you don't talk about it, except if you're in a big data forum. And then that's the only thing you talk about is the elephant, right? So Hadoop. A couple of things about Hadoop. So first off, big data is about a lot more than just Hadoop. And I think from an HPC perspective, it sometimes gets, the Hadoop MapReduce model sometimes gets poo-pooed as being pretty primitive. I mean, if you think about it, it's really a single superstep in a bulk synchronous parallel model, right? And worse, you're actually beginning and ending that superstep by reading from disk and writing back to disk. So it seems very limiting from a sort of traditional HPC perspective. And it is, but I think the real value here is that it's brought some model of distributed parallel computing out into the commercial world, and people are actually solving real problems with this. So I think that's really a testament to its value, the fact that it actually is being used and can be valuable. But again, it's a mistake to equate Hadoop with big data. And sort of to make that point, I was looking at Teradata, their background recently. They were actually formed back in the late 70s. And for those that remember them, we're doing MPP processing and essentially doing big data. So it was in 1992 that they deployed the first 1 terabyte database, and that was actually at a Walmart. And it's interesting to see that 4 years later, so it took them from 79 to 92 to get to that first terabyte, to sort of deliver on the promise of the company name. And then from there, from 92 to 96, another 4 years, they were then deploying an 11 terabyte database. And then beyond that, to 99, they were up 130 terabytes. So big data has been around for a long time. Now, one of the things that's changed somewhat, this is mostly data warehousing, and I would characterize this as big data, small analytics. So people would be running reports against these and doing some amount of analysis, but the kinds of analysis that's being done now is at an entirely different level, I would say. And in terms of thinking about what big data is broadly, and Moti mentioned these, this idea of volume, velocity, and variety is one way of thinking about characterizing big data. This is not a new concept either. This goes back to about 2000 from Gartner. The idea that, and you can see from this graph, this was an IDC report. There are a couple of things you can see here, that the kinds of data that are being generated now are coming from a huge variety of sources. Some of them are coming from the enterprise. Many of them are coming from the consumer space. But as you can see, it's both variety and also velocity in terms of the increase in volume, and also, I think as Moti mentioned, the requirement for processing this data very quickly. You think about some of the sort of mission critical uses of big data. If you're Homeland Security and you're doing analysis, anomaly analysis, looking at sort of antisocial networks, trying to find bad guys, you want to get that done quickly. So the velocity becomes really, really important. And volume is large for a couple of reasons. One, because of all these sources, but also because people aren't throwing the data away anymore. And I was at a conference in Boston about a month ago, and George Radford from Greenplum made a comment about this fact that no one is throwing the data away anymore. And I liked the comment so much, I actually put it on a t-shirt. It's really cold up here, but I'm going to show you the t-shirt anyway. Right, so don't throw anything away because there's gold there. And I think that's actually quite true, actually. Chaff is the new wheat. Okay, so where is all this data going? It could be going into large SAN storage, NAS filers, local storage. Now, there's a clear trend here from, say, a Hadoop perspective to move, and Greenplum as well, to move towards local storage. And you can see some of the reasons for that from a technical and from an economic viewpoint. What we're seeing here is what you can buy for $1 million, roughly, in each one of these arenas. So in terms of aggregate bandwidth, you're not going to be able to beat having a bunch of local disks attached to a cluster. And then as you scale that cluster, you're scaling the available bandwidth. So it's kind of logical to see that motion in that direction. I think there's actually value in each of these approaches for different sorts of things, but there's definitely, as I said, a clear motion towards the local storage for very big data. Okay, so why does VMware care about big data? I mean, clearly the biggest reason is that we have customers that care. And if you look in the world today at roughly, I think Gartner says roughly 50% of all the workloads that are running in data centers worldwide are running in virtual machines at this point, which is pretty amazing. And about 80% of those virtual machines are VMware virtual machines. So, we're a big player in that space. We have a lot of customers. And so it's a logical question from their perspective, can they actually run these sorts of workloads in a virtual environment? And I'll run through a scenario there briefly in a minute. The other reason why big data matters to us is because we're building this huge scale-out platform that, and others were talking about, these cloud infrastructures will eventually be running millions of virtual machines in them. If you think about them as a platform that is generating data, looking at hardware telemetry, looking at telemetry from every level of the virtual stack, it's really important for us to be able to do things like anomaly detection and understand what's going wrong in a data center at any particular time, because we're quite serious about delivering on this vision of an automated data center, which you really do need if you're going to be running at that scale. And actually, as a slight side note, someone yesterday on one of the panels made a comment about an automated data center being sort of a pipe dream. I don't think that was the word that was used, but I think it was sort of dismissed as something that's not possible. And I guess the one thing I want to say, as an HPC person, as Galen mentioned, I've been doing HPC for a long time. It was a really eye-opening experience to join an enterprise company and to realize that the HPC environment is a tiny, tiny niche. It's $24 billion all in. When if you go and look at what's on the enterprise side, there are hundreds and hundreds of billions of dollars at stake there. Probably $1 trillion easily, actually, if you all in hardware and software. So the scales there are totally different. And the reason that matters is because the level of investments from vendors in the enterprise space absolutely dwarfs anything that's being done in HPC. So something that may seem impossible from your perspective because you're looking at it sort of from an HPC perspective, I think is actually quite possible given enough resources to be accomplished in the enterprise. And there's a longer story there, but I digress, so let me move on. Okay, so virtualizing Hadoop. There are two different ways we could do this in a virtual environment. I think one thing I should say is that virtual environments, generally speaking, use some kind of shared storage, typically a SAN storage. And so one way to do this would be to use the virtual machines that are attached to each virtual machine in your cluster and host those on the SAN storage and then run HDFS across that. So you're violating the architectural view that Hadoop has of the world, but you're putting it on high value storage that has high resiliency, et cetera, et cetera. You're totally doing away with this whole thing related to topology awareness, et cetera. The other way of doing this would be much more straightforward. Would it be actually have local disks in your virtual environment and then use those for storage of HDFS? So maintain the HDFS model, the Hadoop model, and just run virtual machines on top of that. So the bottom one, the one where we're using shared storage, is one that is extremely important to our customers. They want us to explain to them and give them best practices for taking advantage of their existing infrastructures. But the one that I think is more interesting here and more interesting to me was looking at true local storage and seeing how well we can do compared to bare metal. So we did admittedly a small test. We took a 7-node cluster, dual socket Westmere systems. You can see the details up here. And the important thing is we ran 3 different scenarios. Each scenario was running the same problem size. We ran this cluster as a 7-node physical cluster. And then we ran it as a 7-node virtual cluster. So one virtual machine on each node, each virtual machine using all of the hardware resources I'm almost done, using all the hardware resources in that physical machine. And then the third way that we ran this was that we ran it as a 14-node virtual cluster. So 2 virtual machines per physical machine, each one using half the physical resources. And again, all 3 instances we ran the same problem size. We ran a variety of benchmarks. We ran everything. So Pi is pure computation. TestDFS.io is really an I/O benchmark. TerraSort has different phases to it. Some of them are one is an ingestion phase where you're just pulling data into HDFS and populating your HDFS from an external source, and then you're doing sorting. So there's a fair amount of processing and I/O that's going on there. Okay, so the way to read this, let's look at the blue bars first. Lower is better. If it's 1.0, then native and virtual performance are the same. If it's under 1.0, then virtual is doing better than native. And so what you see for the blue cases is that we're, for the most part, running a little bit slower. So the 7 virtual machines against the 7 physical machines is running a little bit slower on the same problem size. The more interesting thing is to look at what's happening with the orange bars. You can see that in most cases, it's actually running faster virtualized, which is pretty interesting. I think a lot of people think virtualization slows you down. And in a lot of cases, there may be a 1 to 5% performance degradation, but sometimes we have situations like this. What we posit is going on, we're not absolutely sure, is that by breaking this node up into smaller pieces, we're essentially taking some resource pressure off of each of the Linux instances and the JVMs that are running in each of the OS instances. And it allows us to make better use of the underlying hardware resources. There's possibly also some NUMA effects here. but we think that that's actually less the case. Typically, that will occur when we map a virtual machine onto a socket. So a Linux instance, for example, is trying to deal with the NUMA aspects of running across both sockets, and we've got a VM on each socket that is completely uniform memory. That doesn't seem to be what's going on here. So I just wanted to share that, that we can deliver good performance. Obviously, that needs to be scaled up. And then for our customers, we also need to go look at shared memory as well. I mean, at shared storage as well. OK, so second to last slide. In terms of interconnects, I would really defer to DK on a lot of his details. But looking at what we've seen, bandwidth can often be important. I'm trying to think about how this relates to the RDMA community. It can often be important. In many cases, you'd like to think that the mapping of compute is directly accessing local data in all cases. That turns out not to be the case. In many cases, you're accessing the data on the closest node, and that could be maybe 50% locality. So there's still a lot of blocks of data potentially flying around during your computation, and those are big blocks, so bandwidth could matter there. It matters a lot what the algorithm is and what the workload is that you're running. If your input is pretty much as big as your output in your Hadoop cluster, in other words, if you're doing some kind of data transformation, then there's a lot of data flowing through those intermediate, through the shuffle phase. And there, bandwidth is clearly going to matter. But if you're not, if you're doing something like counts or some kind of aggressive reduction where there's not a lot of data making it past the map phase, then it's less clear that large amounts of interconnect are going to help you there. And then generally the observation, which I think isn't rocket science, is that as you've got a bigger node, you really kind of want to impedance match that big node and all the processing that is doing on it to a beefier network. Latency, I think, is a lot less clear. We didn't really see latency sensitivities in Hadoop, except in, as I mentioned earlier, in TeraGen, where you're actually loading very large amounts of data into HDFS. In that case, building the replicas actually seems to have a latency component to it. And we can talk more about that if people care. The one last thing I wanted to mention was Pregel, which I don't know if people are familiar with it, but it came after MapReduce, also from Google. So the interesting thing about it, it's a graph processing package. It was motivated and inspired by the VSP approach, and it's vertex oriented. So you write code that runs at each vertex simultaneously during a superstep, and messages are then sent from each vertex to whichever connected nodes they want to send messages to. In the next superstep, the messages are delivered and everything just repeats. So a couple of things about that. It's fault tolerant, and I totally agree with what Peter Brahm said yesterday. If people are writing stuff in the future and they're not including fault tolerance, fire them. It's just crazy. So in terms of scale, just to give you an idea, we like scale in HPC. What they're showing, and this is from their original Pregel paper, the bottom left graph is showing, on the right-hand side, the biggest graph that they ran. This was a shortest path algorithm. It's a billion nodes in vertices in the graph and 170 billion edges. And it ran on a 300-node machine in about 10 minutes, which I thought was pretty cool. Now, there are a lot of messages being kicked out at every superstep here, and I haven't looked at this in enough detail to know for sure, but I think there's a lot more potential value for a high bandwidth and low latency interconnect to play a value here, above and beyond, obviously, CPU offload, which is clearly pretty important across the board. Last thing I just wanted to mention, on the right-hand side, this is just more amusing than anything else. On the right-hand side, this is the PageRank algorithm, which really forms the basis of Google's business. This is the magic that they use in their search engine. That's the entire PageRank algorithm written in Pregel. So I calculate based on the market capitalization of Google that code is worth about $14 billion per line. So it's pretty cool. That's it for me. Thanks.
Thanks, Josh. All right, so we'll ask Melinda to come up next, and I think I'll jump right back into the presentation. All right. We'll jump right into the presentation. We've got 20 minutes left, 2 presentations. Thank you.
Hi. When I got the questions for what he's going to ask me, I basically said, I'm not going to answer any of those. Right? I'm basically going to make, I mean, most of the questions were, okay, what do you see in the system architecture? What are the changes that are coming because of this whole big data ecosystem? And I basically said that I will let the audience decide what changes are coming. I'm going to describe what I see as the prominent use cases and why this whole big data term has come about and stuff like that, right? Okay, so there was a earlier panel discussion where actually a very important point was mentioned that, you know, in this whole deciding on the protocols, etc., the application developers need to be involved, right? And this is what I see, that the whole big data ecosystem is actually being driven by the applications. It's not coming from the platform. I mean, if you see the major adopters of Hadoop or any of these NoSQL ecosystem, these are first the users of that ecosystem. The users developed these platforms, and then the enterprises caught on and sort of tried to commercialize it and stuff like that, right? So what has happened is essentially the whole new term of data science, which is essentially combining data analytics, data collection, whatever you have, with machine learning, because now you have tons of CPUs, tons of system resources to throw at such a computationally expensive problem. So machine learning on big data sets actually became reality, right? So these are essentially the workloads that are driving these systems. Analytics and reporting, like the way Teradata was doing it for last 30 years or last 25 years, or Greenplum was doing it for the last 10 years, those obviously remain very important now, and obviously have grown in scale because of the data has increased. And the third thing that we are seeing is, when you analyze all this big data, this data, you have to explain it to somebody about what you are seeing in that data, right? So visualization is actually proving to be a very important topic, right? So earlier visualization techniques, which is like pull all the data out of the database, then create a picture out of that and show it to the user. That's gone, because now you are pulling 10 terabyte and you are showing a 640 by 480 picture, right? Why not just create these individual slices of 640, 480 pictures in situ, in the database itself, and get these pictures then overlap with each other and create a new picture. That will reduce your communication, right? So the in situ visualization is actually becoming a very important application now. All right. So what is this data science that people keep talking about? Well, we can, this is actually the definition comes from Hilary Mason, who is chief scientist at Bitly. Bitly, those URL shorteners. So she basically said, okay, you can split it into 5 steps. Obtain the data, scrub the data, explore the data, create a model from it, and now interpret that model. Okay? So what does obtaining mean? You need to create gather large amounts of data. The more disparate sources these data sets come from, the better, right? So what does this mean? You basically have collected data about your users, right? In the retail space, for example, these are the actual customers that come in, and they purchase stuff from you, right? But then you also have now access to several external data sets. What people are talking about, what people are describing on their blogs, on their tweets, on their Facebook updates, those are all available to you, right? I mean, and people will just give it to you, their Facebook account, and you can scrub it from that, right? So multiple independent sources, gathering all that data, correlating that, and trying to determine unique records, the truth about every user, that becomes important, right? And obviously, since you are going to be fetching these data sets again and again, you need to automate this. You can't basically say, you know, every time I get a disk from Twitter and I basically load it there, right? Obviously, there are some places or there are some cases where you have no choice but to get the large amount of tape or disk and actually load it onto the cluster. But you need to automate for these streaming kinds of data sets, right? Scrubbing. Raw data that you obtain is always messy. There are fields that are, you don't know what they are, what they mean. There was a customer of ours, basically a large bank, which had acquired 14 different banks over its lifetime, and there were records in the customer database that said age 99, and there were something like 70% of their customers were aged 99. Okay, nobody knew what that 99 meant. Every bank meant different. I mean, either the user did not supply it, or something was wrong, maybe given an invalid value, or maybe the user is really 99. You don't know, right? So real data is always messy. You need to clean it up. People describe New York as New York, NY, Big Apple, whatever, right? And now you need to figure out just from this text. So what keeps on happening is your dictionaries keep on growing. You are basically saying, okay, by the way, NY, New York, Big Apple, everything refers to the same city, right? So now your dictionaries, the side data sets that you're looking up, they always keep on increasing. And one of the common ways of scrubbing these data sets, obviously someone like LinkedIn or Twitter is not going to employ 100 people just scrubbing their data. What they do is they essentially employ Mechanical Turk in Amazon basically says, I'll give you 5 cents if you basically say IBM means International Business Machines. I mean, these two things are equivalent, right? And there are like thousands of people here, India, China, everywhere, they're basically sitting in Mechanical Turk and saying, okay, IBM is International Business Machines for 5 cents each. And that works perfectly well, right? They don't have to actually employ those people. So after you have scrubbed this data, after you have cleaned up this data, the third thing that needs to happen is, what is that data telling you? Right? Exploring these data sets is essentially take any 2 dimensions, try to do a scatter plot among that, and basically see, okay, are these 2 dimensions really independent, or is one dimension just completely dependent on the other? Do you see a straight line, or do you really see it scattered? In that case, if you do really see it scattered, in that case, those 2 are not correlated, so are actually good signal carriers. Whereas if they are very highly correlated, you would just take one thing, one column out. That is not adding any more value. So a lot of this exploration needs to happen before you actually start building your models, right? Now, one of the things that is missing in this is that while this exploration is happening, and here actually in situ visualization actually plays a big role, right? But once you do this, I mean, this is some data scientist sitting out there, some statistician sitting out there trying to analyze this data. But once he or she has analyzed it, needs to make a note of it associated with that data set. Otherwise, the next day somebody else comes in, he or she will be doing the same exercise again, wasting a lot of people's time, right? Data set annotations, keeping a lot of metadata about all these vast data sets that you have. So that's a big challenge, right? So once you have that, then statistical modeling is a very, very well-known field. Obviously, there are more advances coming in there. Essentially finding correlations between the past. So you take a very nice training set, as you call it. You label that training set. Again, use crowdsourcing or something like that to label that training set, and now create a model based on that. Try to apply that model to this large data set that you have and see if actually some of those predictions come true. If the predictions come true, then your model is good to go, right? Now, more and more what we are seeing is that a single statistical modeling technique is not good enough for people, right? Maybe it gives 85% prediction rate. That's not good enough. People basically want 95, 96%, even more. So what people have started doing is something called Ensemble Models, which is essentially a model of models, which says you train these 20 models on that, and based on how accurately each of those predicts, give each of them a weight, so that now you have a model which is a weighted average of of 20 models, right? So this now becomes a trivial parallel processing algorithm. I mean, one of the times when we went and early days of Hadoop, when we were deciding what resource manager to use, and we went to University of Wisconsin, Madison, and talked to Myron Livney, who is the father of Condor, and we basically were telling, this is not really a very fancy system that we want to build. It's a very embarrassingly parallel system. And he basically says, oh, we don't use that term here anymore. It's a pleasantly parallel system. It's nothing to be embarrassed about it, right? So this thing, the ensemble model, now essentially becomes a pleasantly parallel system where on these huge data sets, you are training 20 models simultaneously, right? And that's what the simple systems were built because the applications were simple. The amount or the kind of parallelism that were present there was not very complex parallelism. It was really very, very simple parallelism. All right. So once the models are built, they are obviously interpreted. Otherwise, you would see that Washington Redskins winning the last home game means the setting precedent will win next year. Those kinds of models emerge. You don't want that model, right? You need some sort of a domain expertise to interpret those models and improve those models. All right. So the data science data flow essentially comes from raw data, which is huge. Then you derive some data from there in order to make judgments about that data. You build models. Based on those models, if you are going to be using those in the serving systems in order to serve results to the users, then you need to build indexes, because you can't go searching on 10 terabytes of data just in order to serve a single result. So based on all these, now you can essentially see that big data and this just focusing on one paradigm, which is Hadoop, is not going to help you at all. How do you do the serving using these big indexes, right? You cannot. All right. So what plays into this is obviously data diversity. You have graphs, you have natural language text, you have that text converted to bag of words, you have dense matrices, you have, because of the location that is coming from your iPhones and mobile phones, now you have GIS. And the tools also, we have massively parallel databases. We have this so-called big data ecosystem, NoSQL, Hadoop, right? And we actually use the low latency message passing. In fact, most of the algorithms for machine learning, even in Google, who have this GFS and who have this huge MapReduce infrastructure, some of those algorithms are actually written using MPI, okay, on fast networks, because they are actually better to be implemented in MPI, more efficiently implemented in MPI. So use the right tool for the right job is what people have been doing all over. So that basically means that you cannot be completely focused on Hadoop if you are just considering this entire big data ecosystem. You have to consider everything and do a mix and match and have sort of a, what the marketing term for Greenplum calls as unified analytics platform. This is a completely unified platform that, depending on whichever structured, unstructured data, whatever execution model that you want to use, you should be able to use it on the same set of resources, right? And I call it a polyglot frameworks, because people are, you can't say that everyone in the world will have to start using C and MPI or Java on the other side, right? You need to have 10 different languages, 10 different types of frameworks to be supported in the same thing. And that's pretty much it. I think I'm not going to go over much deeper into that. Thanks.
Thanks, Milind, for giving us, I think, giving us a very unique perspective into some of the challenges in big data. We always think of it in terms of infrastructures, right? Hadoop and key value stores, but seeing how these are put together to actually solve a real world problem, I think, is very beneficial. So up next, we have Sumanta. Thank you for joining us from Oral.
Thank you, Galen. Okay, so some of the questions that you asked, I will try to answer towards the end, because I kind of thought they were interesting questions. Too bad I didn't get them earlier. Okay, all right. So let's see. Okay, so this is the standard stuff. Okay, so the first time I sort of, I'm a database guy, and this big data business, I mean, what is this? It's confusing to me. I believe all data to be in one place. What is this business of sharding? I know it never works. What kind of a brain damaged idea is this, and so on. But it has been. I have to admit that it has been a learning experience for me for last couple of years, as we are hurtling towards finding solutions, and exactly what Milind was saying, that that this is an ecosystem that has existed for a long time. And I think Josh said that there was Teradata, it was a big data system, and then we also have got offerings in the data warehouse space, and so on. So the solution that we came up with is actually the kind of stuff that Milind was talking just a few minutes back. That data comes from myriad of sources. It is not simply your bank accounts anymore, or your insurance data structures. It is coming from all these sources. So So the biggest part is what we call the acquire part, or it is also in the old database terminologies. We had a process called ETL, that is extract, transform, and then load into the database. That's is what we used to do. And so okay, so these are the new terminologies. The same ideas, similar ideas. So now, typically, what happens is that the big difference that I see is this: that the ETL processing used to be a hugely time-consuming and expensive process in capturing data into the database. It was very, very expensive. So I think again, in practical matters, what has happened is this: that in this cheaper boxes, that can acquire and cleanse data very cheaply is the way to go. And then once the data are actually cleansed and transformed, that is the cheap CPUs that we can use in this big data appliance. Then we can actually load it into the database. And again, this is where InfiniBand comes up very nicely and fits very nicely. So imagine that you have your Hadoop files, and you can export that as NFS. And we have got NFS RDMA working, and you can just bring the data very cheaply into the database. Now, once you have actually captured the data, then it becomes part of a table and SQL and so on, and so now you can cut, slice, dice any which way you want. You can use OLAP, and again, we have got this another system which is again connected with InfiniBand, which is called Xalytics. So there, people have put stuff like R, to actually, these are statistical package. Again, something that Milind was mentioning a while back. So again, this is a complete end-to-end, solution that, we find a practical way of delivering to our customers. So again, these are some details. I'm not going to, go too much into it. So let's sort of, talk a little bit about the big data. Okay, so for me, big data means lots of storage, lots of data flow, lots of computes. We want to avoid all the communications to scale. We just heard a little debate about, TCP coming into the, foray, and, how, RDMA came to the rescue and stuff like that. All those cool things are happening. And, we want to avoid synchronization, and, it's kind of interesting. I've never seen it actually happen, but okay, so these are all interesting concepts, and seems like it works most of the time. Now, here is what I saw. So people had put together these nice big data appliance and so on, but the first time I sort of saw the statistics, it looked like we are still communication bound. I said, what happened over here? I think DK also mentioned this, and so it was there was just too many inefficiencies. What I found was that there were lot of algorithmic problems. There were there was constant shuffling of data that was going on in between, and so the good news in all of this stuff is that InfiniBand came to the rescue, because it sort of it became a savior, because a lot of the algorithmic inefficiencies were hidden by the sheer brute force of that is available with InfiniBand. So now we have got, all of us have got a lot of work ahead of us in terms of making the algorithms a little better, like some of the shuffle thing that that Mellanox has done. It sounded cool. I'll have to look into it a little bit. I'm sure we are all paying penalties, of that kind. Okay, so let's see. So again, these are both of these have been discussed. That we have to have high availability. You have to replicate data. That cost itself. And then there is a time to deploy. And let me see. What did I want to say over here? Optimizing system. Yeah. There are expensive data transfers. This is the dilemma. Map side joins. I took that one particular problem. Can you really shard your data to the extent that it is actually isolated and it can be worked in parallel, like that? Most of the time, I sort of find that that is not to be quite the case. Especially when you're establishing relationships. At the end of the day. So, these are some of the things that I actually wanted to say. And of course, we talked about the bottlenecks of shuffle exchange. I already saw that, and it has been talked about, and looks like I'm not the first guy who saw this. Obviously, there are a lot of issues with the key value store. It is, it is synchronous. It waits a lot of time. What I've seen. And of course, and again, disk I/O is something that we have all talked about. People are saying that, okay, use solid state devices, whether it is PCI or SAS disks. So maybe it will work, but again, right now I think the picture that I showed you in the beginning, if the costs are to be contained, then right now SSD is not working to our advantage. Okay, what else do I have? That's about it. Okay, can you please bring up your your slide? I have a couple of minutes. So. Yeah. So the other one, the storage one. Yes. Yes. Yeah. I actually, I think these are really great questions. And the question is block storage dead? We still have VMS systems. So no, no, there is, there are lots of very smart people working on block storage, so it's probably going to live for a long time. But if I am given a choice, I would actually prefer to use something like an NFS. I like it primarily because, especially the version 4 onwards, it is allowing again the application to actually pass hints. Again, it is bringing the ecosystems which are artificially separated closer together. You can pass hints to the storage systems. You can make the storage system a little smarter. Okay, so there are opportunities in doing that. Now, how do you flexibly support these protocols in unified storage system? I don't have a clue. Okay. Okay. So one thing that I wanted to mention about this virtualized environments, that people have been asking us, that hey, all VMs are not created equal. Okay. So there are VMs and VMs, and so the trick over here, I think, is for VM providers to consider some kind of an I/O resource management policies. How exactly do you dish out the bandwidth? it is not the QoS at the InfiniBand level, but at one level higher. Okay, so that will be one request that I will have for Josh. That please think about it.
Okay, we're done. It works. We have that.
Okay, that's wonderful. Thank you. So, and you can articulate that policy, and it is governed. Okay, that's very cool. Okay, so one other question was, about POSIX. I think that you cannot, wish POSIX dead. You cannot do that. Because people will not use your systems. If you don't have POSIX semantics. This is something that I have seen, over and over again. That something that is so universally used and people depend upon it. They may not know it, but they depend upon it. So I think it will be, short-sighted to kill POSIX.
So actually, Sumant, do you think the full POSIX specification is implemented anywhere in the scalable systems?
That is true. It is not. But so what happens is that and that's what makes it hard, Milind. That because people have cherry picked it over. So you may have used a FCNTL, to have some behavior, and some file system is giving you that, and all of a sudden, if that behavior is not there, then
you're just eliminating a bunch of ifdefs. That's
right.
Basically what is happening.
Exactly. All right, and that's about it. Thank you.
Well, let's thank our panelists. I think we're right up to the next talk.